3 hours. That's how long the interstellar comet 3I Atlas vanished with no light, no trace, nothing. Then, when it came back, it was moving almost twice as fast as before. NASA's data didn't match. Telescopes caught strange readings. Some think it broke apart, others think something made it move. Is this just a natural glitch, or are we seeing something we've never seen before in space? Let's discover. What happened in those 3 hours? One moment, astronomers around the world were tracking an interstellar visitor named 3I/Atlas through the coordinated lenses of the Gemini South Telescope, the Hubble Space Telescope, and the James Webb Space Telescope. Then, without warning, its signal simply disappeared. What could make an object moving through open space vanish so completely from every major observation network on Earth? And even more shocking, how did it come back moving twice as fast? At precisely 2:17 Universal Coordinated Time, the object's visible and infrared signatures fell to zero across multiple instruments. To scientists, the phrase going dark doesn't mean an object becomes literally invisible, it means that its measurable light output, across certain wavelengths, drops below detection thresholds. In simpler terms, the object stops reflecting or emitting light in ways we can record. The timeline quickly became the focus of intense scrutiny. In less than 60 seconds, 3I/Atlas transitioned from a stable, trackable source to absolute silence. For the next 3 hours, from 2:17 to 5:29 Universal Coordinated Time, there was no measurable data, whether from the ground-based observatories in Chile, the orbital instruments circling above Earth, or the automated tracking systems that log celestial coordinates every fraction of a second. Such a synchronized blackout across multiple platforms is extraordinarily rare. Astronomers who have spent decades studying transient phenomena struggled to find any parallel. Even comets that fragment or spin out of view still leave faint traces, scattered signatures, or dust tails. Then, at 5:29 Universal Coordinated Time, the universe blinked open again. The object reappeared, but it was not the same. Its position in the sky had shifted far more than models had predicted. Even more startlingly, its apparent velocity had doubled relative to the previous recorded interval. Instruments from the James Webb Space Telescope and the Very Large Telescope in Chile confirmed that the object's trajectory no longer aligned with earlier projections. For astronomers used to predictable orbital mechanics, this was like watching a train jump tracks mid-route and continue forward as if nothing had happened. At first, scientists scrambled to explain the anomaly. Early analyses suggested that sensor recalibration could have temporarily altered readings. Space telescopes, after all, rely on complex alignment systems that adjust for thermal drift and signal interference. But recalibration alone could not explain why multiple independent instruments, operating in different wavelengths and controlled by different teams, reported the same gap in data. Another possibility emerged, that the object had undergone a sudden burst of outgassing, jets of volatile material erupting from beneath its surface, propelling it forward like a natural rocket. This has been observed in comets before, though usually accompanied by visible debris or gas tails. Yet 3I/Atlas showed none of the expected visual signs. As scientists debated the cause, NASA issued an official statement. The agency confirmed that the anomaly was under active investigation and that all data from the relevant instruments were being re-verified. Back in the year 2017, the first known interstellar visitor, Oumuamua, had sparked similar controversy. Its unusual acceleration and cigar-like shape led some researchers, including Harvard astrophysicist Dr. Avi Loeb, to argue that it might have been an artificial probe. That claim was widely debated, and most scientists favored natural explanations such as ice sublimation or tidal fragmentation. Yet the debate never fully died. Then, in the year 2019, the second known interstellar object, Borisov, appeared, a more traditional comet that fit expected models. For a time, the mystery seemed resolved until 3I/Atlas entered the picture, and the internet erupted. Amid the noise, some credible voices emerged. Dr. Avi Loeb urged the scientific community to investigate with an open mind. He noted that while there was no direct evidence of artificial origin, the combination of disappearance and acceleration made 3I/Atlas an outlier worthy of further study. Other scientists echoed his sentiment, emphasizing that anomalies, however rare, often lead to breakthroughs in understanding the universe. For researchers accustomed to the slow, steady rhythm of celestial mechanics, the event was both thrilling and unsettling. The laws of physics do not usually make exceptions, and when something appears to break them, even briefly, it demands attention. Some theorists proposed that the blackout could have resulted from an unknown form of dust or plasma interference. Others speculated about gravitational lensing, that light from the object might have been temporarily bent or obscured by a dense, unseen body passing between it and Earth. Yet, as more data came in, none of these explanations fully fit the observed acceleration. As one astronomer put it during a press briefing, the question isn't what we lost sight of. It's what came back. The journey that shouldn't be possible. Under the silent skies of Chile, on the first day of July in the year 2025, a telescope designed to watch for deadly asteroids found something that should not have been there. The system was called the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a robotic network built to spot threats heading toward Earth. But on that night, it captured something stranger, a faint, fast-moving light emerging from the direction of the constellation Sagittarius. Within hours, astronomers realized this was not an ordinary comet. Its speed, its angle, and its trajectory all pointed to one conclusion: this object was not born in our solar system. It came from somewhere else entirely. The initial readings shocked observers. Even for a comet, 3I/Atlas was moving incredibly fast, about 60 kilometers per second relative to the Sun. That's fast enough to circle the entire Earth in just over 10 minutes. Its orbit was hyperbolic, meaning it wasn't bound by the Sun's gravity like most comets or asteroids. Instead, it was on a one-way journey, swinging past our star before continuing into interstellar space, never to return. Astronomers confirmed this within days, calculating that its inbound path had originated from far the solar system. This made it only the third known interstellar visitor ever detected, following the mysterious Oumuamua in the year 2017 and the comet Borisov in the year 2019. Each had arrived unexpectedly, each unlike anything seen before, and now, the pattern had repeated for a third time. The difference was that this one would behave in ways the others never did. In the weeks following its discovery, telescopes around the world began to focus on the new arrival. The Hubble Space Telescope set an upper size limit of roughly 5.6 kilometers across, placing it within the range of an average cometary nucleus. But even more interesting were the signs of activity long before it reached the inner solar system. At a distance of about 3.8 astronomical units, nearly 4 times the Earth's distance from the Sun, 3I/Atlas was already awake, releasing gas and dust in thin, curling jets. Most comets remain dormant at that range, frozen and inert until the Sun's warmth stirs them closer to Mars's orbit. This early activity suggested that its composition was unusually volatile, rich in compounds that evaporate at much lower temperatures than normal cometary ice. Then came the compositional surprise. Spectroscopic readings revealed that the ratio of carbon dioxide to water vapor was roughly 8:1, an extraordinarily high value compared to typical comets, which usually contain far more water than carbon dioxide. In simple terms, this meant 3I/Atlas was unusually dry, or perhaps that its outer layers were dominated by carbon-based ices rather than water ice. This kind of chemistry hinted at very different conditions in the region where it formed, perhaps a colder, darker part of another star system's disk, or even the debris field of a shattered planet. The James Webb Space Telescope's infrared readings confirmed this imbalance, while polarization data, a measure of how light scatters off particles, showed that its dust grains were unusually compact and reflective. That suggested a denser surface texture, possibly with metallic or silicate inclusions that made it shimmer more efficiently under sunlight. To planetary scientists, that was deeply intriguing. The signature didn't match any known cometary family in our solar system. By late July, 3I/Atlas had become one of the most intensively observed objects in space. Different instruments studied it in different ways. The Hubble Space Telescope captured visible and near-ultraviolet images to track its coma, the glowing halo of gas and dust that surrounded its nucleus. The James Webb Space Telescope, working in the infrared spectrum, analyzed its heat emissions and chemical fingerprints, revealing not only the carbon dioxide to water ratio but also trace compounds of methane and formaldehyde. Meanwhile, the Swift Observatory monitored it in ultraviolet light, detecting the faint glow of hydrogen atoms released as sunlight split water molecules in the comet's tail. Even orbiters around Mars, such as the European Space Agency's Mars Express and the ExoMars Trace Gas Orbiter, joined in, providing side-angle views that helped scientists build a three-dimensional model of the object's path. The coordination was global and continuous, creating a moment in astronomy when nearly every major instrument on or around Earth was focused on the same distant traveler. This vast network of observation was what made the later blackout so puzzling. Because so many instruments were watching from different angles, a simple technical failure couldn't explain why the object vanished from all of them at once. But understanding how these instruments work helps reveal why such a blackout might appear. Telescopes detect light that has traveled across vast distances, and even small changes, like a burst of dust from a rotating surface, or a fragment breaking off, can temporarily obscure the nucleus. If 3I/Atlas released a dense cloud of fine particles while spinning, it could have briefly hidden its light behind its own debris. From our perspective, it would look as though the object had gone dark. When the dust cleared, the reflected light would return, possibly stronger if the outburst exposed fresher, brighter ice beneath the surface. That explanation remains one of the most scientifically plausible, even if it doesn't fully account for the sudden speed increase. But why does any of this matter? Because interstellar objects like 3I/Atlas are messengers, not in the poetic sense, but in the scientific one. They carry physical samples of material that formed around other stars, in other planetary systems, billions of years ago. When such an object passes through our solar system, it gives us a fleeting chance to study matter that has traveled from another corner of the galaxy. Every element in its composition tells a story about how planets form, how solar systems evolve, and how the building blocks of life might spread across space. Some scientists believe interstellar comets could transport organic molecules, the complex carbon-based ingredients that lead to life, between worlds. Others think they might be fragments of destroyed planets, flung out into the void by gravitational chaos. That's what makes this discovery so important. For only the third time in human history, we are directly observing a piece of another star system, and this one is behaving in ways that defy easy explanation. Don't forget to like, comment, and subscribe.